My name is Heng with the matrix number A200497. Today, I would like to present the simulation assignment. For the question 1, the question is asked to model the CSTR and find the transfer functions. Before we do the calculation, we need to make a few of assumption, which is the liquid is incompressible and the constant liquid density. The fluid is perfectly mixed. Constant heat capacity, heat produced by system, heat added, and then different volume of a 3 CSTR, different inlet flow rates of fluids. The overall inlet and outlet flow rates are constant, which is in the steady state condition, and then we assume that there's no heat loss to the surrounding. Okay, for the general equation of the mass balance for CSTR, the general mass balance equation is equal to the rate of the accumulation equal to rate flow in minus rate flow out minus rate of reaction. For the component A, the equation can be expressed as like this, equation 1.1. Then for energy balance, the equation is the rate of energy accumulation equal to the rate of energy in minus rate of energy out plus heat added plus heat produced. It also can be expressed like the equation 1.2. Then for the first CSTR, we need to find the transfer function in terms of concentration, which is by using the general equation of the mass balance. Then the mass balance equation is divided by V1. Then for the steady state condition, we assume that the differential CA1 over dt is equal to 0. Then we subtract the equation 1.4 with the equation 1.5. Then we get this equation. For the steady state equation, the concentration A naught will have a bar above the C. Then for the small perturbations around the steady state condition, the equation will be used and substitute into the equation 1.6. Then we can get this equation. After that, we take the Laplace transform and then arrange it into this. And then we simplify the equation. We can get the transfer function GC1. And then we insert the value into this transfer function. For the transfer function in terms of heat added and the inlet temperature, we use the energy balance, general equation of energy balance, and then we divide it by this raw CPV1, and then also in the steady state condition, we assume that dt1 over dt is equal to 0. Then subtract equation 1.15 with the equation 1.16. Then also for the small perturbations around the steady state condition, we substitute these three equations into the equation 1.17, then we can get this equation. After that, for the transfer function with respect to Q, we assume that the T naught is equal to 0 and then the CA1 is equal to 0. Then by taking the Laplace transform, we arrange it and then simplify, we can get the transfer function GQ1. Then for the transfer function with respect to T1 minus I minus 1, we assume that the Q is equal to 0 and CA1 is equal to 0. By taking the Laplace transform and rearrange and simplify, we can get the transfer function of GT1. Then for the second CSTR, also same with the first CSTR, you need to find the transfer function in terms of concentrations and the transfer function in terms of heat added and inlet temperature. For the transfer function of energy balance, we have with the respect to Q and with respect to T I minus 1, then we get the transfer function. But for the third CSTR, since the reaction in the CSTR is the second order reaction, then the material balance is not similar with the previous one, then this is the general equation of the material balance of the component A in the third CSTR. Then we divide that by the V3 at the steady state condition. Then we need to linearize this equation by the Taylor expansion to remove the square here. Then by taking the Laplace transform and rearrange and simplify, then we can get the transfer function GC3. Then for the energy balance, the transfer function in terms of heat added and inlet temperature at the steady state condition. Then also we need to linearize this equation by Taylor expansion. Then we can get the transfer function with the respect to Q with the respect to T I minus 1. So that for the overall transfer function of concentration, since the three CSTR are non-interacting system arranged in series, then the overall transfer function for the mass balance is the product of these three individual transfer functions. So the GC is like this. Then for the overall transfer function of heat added, also GQ can be GQ1 can be multiplied with a GQ2 and GQ3. Then for the overall transfer function of inlet temperature, also the GT will be equal to the GT1 multiplied with the GT2 and GT3. Okay, for the question 2, the question asks to create a column in the MATLAB of Simulink using the transfer function we find it in the question 1. Okay, then so that we need to design a block diagram of the system by using a Simulink. Okay, from the Simulink, the purpose of we create the Simulink model is to represent the dynamic behavior of the three CSTR in a closed loop control system. And then instead of solving the equation manually, Simulink allows us to simulate the system response graphically so that we can get the response curve after that. Then the model also provides a platform to test the controller performance under different operating condition. Yeah. First, we need to put the controller. In here, I use the BNID controller to control the temperature. Second one is the final control element, and then we also have the sensor of a feedback path to assume that to be ideal, meaning that it has no delay of measurement error. Yeah. Okay. Then for the process of subsystem, is designed by like this. Yeah. Okay. For the question 3, we need to design a control system, servo control system by the manual controller. So that we need to construct a P controller and PI controller and also the PNID controller. After we set the parameter for the controller, then we need to set the step input, which is the initial value is equal to 0 and then the final value is equal to 35. And then we try to run the model. Then we can get the response curve like this. Okay, for the servo controller by the tooth box, we replace the manual one with the tooth box, which is the P controller and PI controller, and then a PNID controller. Then the same parameter is applied to these three controller, and then also the same input is set in the set point, which is the final value is equal to 35 and the initial value is equal to 0. Then after we run the model, then we can get the response curve like this. So we can get we can see the PNID. The PNID is the best one lah to control the system because it's very fast to reach the steady state. Yeah. For the regulatory control by manual controller, since the regulatory control, it means we need to add one disturbance of log, which is u. Here I set the u is equal to 5, so the initial value is 0 and then final value is 5 at the step time of 25 seconds. The same input is applied also. Then we run the model, we can get the response curve like this. For the regulatory control system by the tooth box, we replace the manual controller by the tooth box. Then also same parameter controller setting is applied. Then we set the step input to control the temperature. Initial value same with 0 and then final value is 35. Then after we run the Simulink, can get the response curve like this. Okay. For the question 4, the question asks to repeat the question 3 with the multiple set point and disturbance. So that for the multiple servo control by manual controller, we need to put here I put 3 step input to control the temperature. Then also multiple lot is added into the design controller system. Then for the servo control, there's no disturbance of lot, so all the lot here is equal to 0. Then the stem input, no. Then for the first step input, I set the step time is 15 and then initial value is 30 and final value is 46. Then for the second step input, the step time is 30. Also, then initial value is 0 and the final value is 16. For step time, for the third step input is 50, then the initial value is 0, then the final value is 80. Okay. Then after we run the control system, we can get the response curve like this. Same thing I did for the multiple set points and multiple disturbance for the servo control by the tooth box controller. But here for the servo control, all the logs U are equal to 0. Then the same input are applied. The same input are applied in the control system. Then after we run the Simulink, we can get the response curve like this. Okay. For the multiple set points and disturbance in the regulatory control by the manual controller, we also have a three controller here, P controller, PI controller, and the PNID controller. Then for the regulatory control system, we need to set the multiple disturbance of lot, which is U. For the lot 1, the U is equal to 10 at the step time of 18 seconds. And then for the second one, also final value is equal to 10, but the step time is at the 35 seconds. And then for the third one, is also the final value is set to be 10 and at the step time of 55. Then the same input are applied here for the multiple set points. And after we run the Simulink, we can get the response curve like this. Okay. For the tooth box one, we just replace the manual controller with the tooth box here, PI and PNID. Then also same value of the disturbance of lot U are set here. Then for the same input, we set the same input, same with the previous one. Then we run the Simulink, we can get a response curve for the regulatory control with the multiple set point and the disturbance. So we get the response curve like this. For the question 5, we need to tune the controller with the two tuning methods, which are the Ziegler-Nichols and the Cohen-Cohen. For the Ziegler-Nichols, at first we need to remove the PI and PNID controller, just left the P controller in the active mode. Then we set from the 0, and then we for try and error methods, we try to raise the value of the gain until we get the sustained oscillation curve like this. For example, here I put the value of a KC is equal to 0.845. Then I run the Simulink. We can get the response curve like this, which is the sustained oscillation curve. And then we use the equation here, the three equation here for the PNID controller. Then we can get the value of the KC, tau I, and tau D for the PNID controller. Then we make a design control system to compare the PNID controller with the tuning one and without the tuning. So then we can get the response curve. Then we can compare the response curve with the tuning and without the tuning for the PNID controller. For the Cohen tuning method, we need to remove the connection between the controller and the process. Then we try to run, then we can get a response curve like this. The important one is we need to get this value, which is the 87, which is the BU, and then we need to determine the slope. S is equal to 31.9, and then the M is the value we set for the initial value, which is the 35. And then after the calculation, we can get the TD is equal to 1.4316. And then by using these three equations, we can get the value of the KC, top I, and the top D. After that, we compare the response curve for the PNID controller for server control with the tuning method, which is the Cohen tuning method, and then without the tuning. But here, the tuning method is not suitable for the model because the Cohen tuning will be assumed the first order plus that time model, but for the question, the reaction tank, which is the 3 CSTR system, is a higher order, so that the model will lead to the instability and of the unsatisfactory transient behavior, so making it unsuitable lah. For the question 6, we propose the advanced process control strategy, which is the model predictive control MPC. Yeah. Yeah, that's all. Thank you.